Okay, so the recording has been started. Let me share my screen. Okay. I hope my screen is visible, right? Okay, let me. Okay, so let's keep this one here. Okay, I guess my screen is visible and I'm audible also, right? So let's just start today's session. Okay. Okay. So this is week 7 and week 6. What we did, um, we discussed the workings of decision tree and regression tree, right? And then we briefly touch how to handle missing values. For example, you can handle missing values by replacing it with single value, for example a mean, right? If you know that my attribute has a normal distribution, then the missing values can be represented by its mean, right? Because it will be the most probable value, right? Or mode, let's say most repeating value if it is not a normal distribution. And you can also do something like a linear interpolation between two endpoints of a missing segment, right? Given that the segment is not too big. Okay, so and then we also like deeply discussed theoretically how cross validation work. We didn't do any example of it, so we'll do it today. And so today's kind of overall objective would be to do cross validation on a example, and then go for a for the other topics like bootstrapping, bagging, boosting, or what ensemble methods look like in let's say in practice, and do a example of random forest. So we'll explain what random forest is. Okay, so let's just, so because it's a your week 6 assignment deadlines are over, right? So let's just go over week 5 and week 6 previous assignments, so that if you have any doubts, you can clarify it now. Okay. I hope you have gone through the week 5, week 6 I have uploaded recently. Okay. Yeah, so first question of week 5, and you can just interrupt me and ask me whenever you found something confusing. Okay. So given a three-layer neural network which takes 10 inputs and 5 hidden units and outputs 10 outputs, right? How many parameters are present in the network? So how much it would be? So let me just connect my graphics pad so that it will be easier to visually represent this. And one thing is this parameter calculation and everything are very common in exams also. So just be prepared to have these kind of questions. Okay, just 1 minute. I have to get a adapter. Okay, we are back. So uh, let's just open up. Okay. So it is a 10 input neural network, 5 hidden units, so only one layer, and then it gives. Okay, so given a 3-layer neural network which takes 10 as input and has 5 hidden units and output 10 neurons, right? So how many parameters it would have? Okay. So it's a 3-layer neural network. So first layer, second layer, and the last layer, right? So these are the layers. Hidden neurons, there are 5 hidden neurons here, 5 neurons here, 10 is the output neuron, and it takes 10 inputs, right? 10 inputs. So this is the input layer basically. So here my weight would be how much? 10 times 5, and my bias would be 5. Here weight will be 5 times 5, bias would be 5, or basically 1 cross 5 if I just do it correctly in terms of shape of the matrix, right? And here the weight would be 5 times 10, and the bias would be 1 time 10, right? So how much? 10 times it's 50 plus 5 plus 25 plus 5 plus 50 plus 10, right? So it would be around 100, and then 20, 125 and 35, 145, if my addition is correct. Let me put there. 115. So one thing we missed, maybe, let's see. A 3-layer neural network means including the input layer, I guess. Okay. So if I include the, uh, so one layer would be not there. So let's just omit. This layer would not be there, right? So they have mentioned 3-layer input and 3-layer neural network including the input layer. Okay. So in that case, 5 times 1 times 10, 10 times 5. Okay. So it will, and wait, let me read the questions once again. How many parameters are present in the network? 3 layer, 3 into 5 units. Okay. So here 5 times 10, this would not be there, right? So in that case, 115. So one thing we should remember from this is 3-layer or n-layer neural network mean including the input layer, okay? Including the input layer. So this input layer should be included within the number of layers, okay? Second one, it's okay. So recall tabular, for example from class where we did transformation of features to make it linearly separable. Which of the following transformation can also work? So it would be adding a third dimension z. So how it will work? If I do an and operation, right? And is separable, linearly separable. I not send him the today's meeting link. He should find it on it. Okay. So so adding a third dimension where z is linearly separable would work. Okay. We use several techniques to ensure the weight of a neural network are small, such as random initialization around zero or regression. What conclusion can we draw if the weights of the A and N are high? So one observation could be it So when the neural network has high weights, that means my output is very big, right? So it happens when the neural network diverges. Okay, only when the neural network diverges. Otherwise, it should represent something like a normal distribution. Okay, if all of my neural network weights are high, right? But if weights of the neural network are high, right? All of the weights are high. That means my network has been diverged. So the model has overfit. No, it is diverged. It is incorrectly initialized. It can happen that my model is correctly initialized, right? But my labels are, let's say some label is none or something, right? It creates a non-integer update or non number numerical update. It can also cause my weights to explode to none. Okay, or let's say my targets are so my labels are so bad that my model can reach up to a high weight. Okay, if my, let's say my target is 1 million, okay, then my model weight has to be high, and most of the time it diverges if my targets or labels are not in a correct scale. Okay, yeah, so none of them, mostly it means the model has diverged. uh, Okay, four is if a basic neural network, in a basic neural network, which of the following is generally considered a good initialization strategy? So the general strategy is to initialize with zero mean and a very small standard deviation. For example, in uh, in goal dot initialization for radio activation, it is 1 by the variance should be 1 by n1 plus n2. Okay, so N1 is means the number of incoming neurons and the number of outgoing neurons in a layer, right? And so it is very small. If you see 1 by N1 plus N2 is the variance, so the standard deviation would be 1 by root over of N1 plus N2, right? So the option would be C, initialized with randomly weights with a very small value close to zero. Okay, so my variance is very small, but all the values are close to zero. Okay. Now, which of the following is the primary reason for rescaling input features before processing them to the network? So let me just give you an idea why we rescale our features. Okay, maybe it is already taught in the lectures, but it's good to revisit those concepts. Okay, okay. So let's take a toy example. Let's just draw two parameters. Let's say x and y. X, and let's say x1 x2. Okay, and there is that cost function that we have to optimize, j. Okay, now uh, so one thing I have to tell you before this, let's say my x1 varies from 0 to 100. Okay, and my x2 varies from 0 to 1. Okay, and somehow they have the same importance in predicting y. Okay, same importance. So the weight associated with x1 and this should be whatever the weight is. Let's say if they have the same impact on predicting y, right? If whatever the weight is, my w1 should be w2 by 100, so it should be 100 times smaller to have the same impact on y. That means if I just draw the objective function j with respect to those two parameters omega 1 and omega 2. Okay, so they would be, so omega 1 is, if let's say omega 1 is omega 2 is fixed, then omega 1 would be 100 times smaller. Or if I say omega 1 is fixed, then my omega 2 would be 100 times omega 1, sorry, omega 1, right? So basically that means my objective function, if it is a convex function, it will be stretched. It will be stretched like this. where my this dimension, how much it will vary in this dimension would be varying 100 times more in omega 2 dimension. Okay, to have the same impact on the cost. Okay, so one thing, so how it is represented as a contour plot sometimes. So let's say just the top view of the same picture. Okay, so omega 2 and then omega 1, and then my cost would vary something like this. Okay, and these are the inner, let's say these are the inner, as the cost reaches its minima, this is my contours. Okay, let's say another contour is here, something like this. Now, if my weights are initialized here, my omega 1 and omega 2 is initialized here. If I traverse this terrain, right? So how it will traverse the terrain? Here, the gradient would be much higher, right? Than here. So my weight update would be like this, okay? And here it will say again something like this, and it will go around, so somehow reach this minima. Okay, based on the terrain shape of the terrain. However, if my these parameters x1 and x2 both are like 0 to 1, right? In that case, my omega 1 and omega 2 have the same scale. It should also, let's say, go from 0 to 1 to have the same impact, or 0 to some constant to have the same impact. Then instead of this, um, my cost function top view would look like some symmetry will be there. Okay, omega 2, omega 1, and my cost function would look something like a symmetric function. Okay, yeah. Here, if like exploring this terrain is much easier because now I have a kind of strong symmetric gradient. Okay, which would not, let's say, we don't have to explore a particular dimension more than one other dimension. Okay, so you can just reach the minima really quickly. Let's say here we have to explore something and we came here. Right? So you see the impact. So it's like if one directional gradient is too much, then my resultant gradient is biased toward that direction. Okay, and it hampers my learning. So that's why let's go to that question again. Um, yeah. So to ensure all input features contribute equally to the initial learning process. So why we rescale? Because of this figure, so that my weights are weights are in the same scale and they contribute equally to the learning process, not like one weight is varying in a large scale and it biases my gradient to that direction more. Okay, okay, so I hope it's clear. Now let's another question. 6 in a Bayesian approach, so it's basically how they are named. So this is the posterior probability, okay, and this is the likelihood, this is prior, and this is the your is it D is, yeah, D is the evidence. So it's sometimes is the partition function also. So let's not yeah, this is the evidence of D, just the naming convention. Okay, so this is posterior, this is prior, the theta p theta, this is likelihood, and that this is the evidence PD. Just remember this, uh, it can come in your exam. Okay, so how this Bayesian formula is named. Okay, so why do you often use log likelihood to maximize instead of directly likelihood estimated? So likelihood estimation, what is it exactly, right? So you can think of likelihood estimate being, um, let's say I want let's say there is this X, uh, uh, okay, So how it is formed actually? So let's say we have this data set x1, y1, x2, y2, x3, y3. Okay. Now, what is likelihood is, let's say we model this relationship with a parameter called theta. Okay. And what it predicts, uh, wait 1 minute, just take this call. Okay, guys, sorry for the disruption. Okay, so what is likelihood? So it predicts yi given that theta, okay, and given, let's say, xi, okay, and we want to maximize predicting this yi. So we want to maximize the probability that my yi prediction is correct. So the likelihood, or likelihood, as we know, is actually the joint probability of my model in predicting all the y's together. Okay, so probability of y1 given theta comma x1 into probability of y2 given theta comma x2 into another probability of y3 given theta comma x3, right? This is my likelihood target, that I want to maximize the joint probability of predicting all the y values from the x values. Okay. Now, see, if I try to optimize this objective, if one of my probability becomes close to zero, my entire log likelihood estimate is kind of goes to zero, right? So my entire likelihood estimate goes to zero. So it's a multiplication or pi operation, right? Pi of p yi given theta comma xi. So the problem is, if one component of this entire multiplication operation goes to zero, entire objective goes to zero, right? So it's kind of an unstable objective. To make it stable, what you can do, you can just take log of this, and log is a monotonically increasing function. Okay, so that means log and the log likelihood and likelihood, if I increase them both, so if I increase the log likelihood, that means I am increasing the likelihood. Okay, so just taking log of this would result in summation. So inside log, if it is multiplication, outside log it is summation. So summation of I log of p of yi given theta xi. So just ignore my writing, it's very bad. I guess the driver is not installed for this. Okay. So here you see, if one component becomes zero, the other two are not disturbed, right? So it's the log likelihood is kind of more stable, right? That's the reason why we take log after the likelihood function. So C is log likelihood products turns into sums, making the computation easier and more numerically stable. That's the reason. Okay. Now 8. In machine learning, if you have infinite amount of data, but the prior distribution is incorrect, will you still converge to the right solution? Yes. So you will. So if the data is infinite, the prior would have very negligible info, like influence on the on the convergence, because it will be dominated by the posterior, yeah, by the likelihood. Okay, so yeah, inferior data, if the influence of prior becomes negligible, it will converge to the true underlying solution. Okay, so the A would be the answer. Okay. Then the ninth, the threshold function cannot be used as an activation function for hidden layers. Reason the threshold function do not introduce non-linearity. Okay, so the threshold function is that function we have shown you uh, for the biological neurons, right? This function. Oh, wait. Yeah, so threshold function looks like, so if this is x and this is y, my threshold function would look like this. Okay, so it's a step function basically. So the answer is true, and reason is false. So it introduce non-linearity, right? It is a non-linear function, right? But the statement is true. Why? Because we cannot calculate the derivative of this step function, right? Because it is you can see from the picture, it is not derivable at this point, at x equal to this, right? Because it has a steep change, right? It's a sudden change, so it's discontinued at x equal to the threshold th, whatever it is. So we cannot have a kind of a smooth derivative here, right? So the gradient computation would not be possible. So not like it is not introduce a non-linearity, it is introducing a non-linearity, but the it cannot be used for neural networks because we cannot compute uh, this gradients, right? So cannot backpropagate the errors. So last question is this MLE MAE. It's kind of a factual question. You can also see in the literature, if you can, right? And the MLE is actually so from definition, MLE is kind of a special case of MAP, right? So it's like its maximum a posteriori or something like this, or this is MLE is maximum likelihood estimate. And when the MAP has a prior of uniform distribution, it will be converted to an MLE. Similarly, MAP act as a regularized form of MLE. Okay, so these are factual things. It's just to remember this. Okay, let's go for question 6. So you are supposed to compute the entropy of a 90 to 10 split between two classes. Okay, so it's easy. So let's just do because this type of questions can come, right? So let me just work it out for you. Uh, so it's a two class, let's say A and B, right? And you have 90% here, 10% here. What is the probability? So what is the probability? P of A is 0.9 and P of B is 0.1. Now my entropy is what? Summation minus P of X log of P of X, right? So summation over X, right? So you just do minus 0.9 log of 0.9 plus 0.1 log of 0.1. That would be your answer. So and this is log base 2. Okay. So what would be your answer? It will be A 0.469, something like this. Now consider a data set with only one attribute. Suppose there are eight. So these are see, the equation is also given. So if there are 8 possible values, right? And you are supposed to split into two, let's say two subsets. The possibilities are 2 to the power q minus 1 minus 1. Okay? These many possible splits you can have. Okay, so how it is coming is you you choose or not choose all the 8 possible values, right? But one value you have to choose. With that, you can choose or not choose, because there can be two possible splits, right? You can choose or not choose another value, right? So there are many 2 to the power 7 choices you have, and then -1 means you are not choosing that set where you have, let's say, all the values chosen to one particular set. Okay, so just to not have that second set empty, that is this -1, minus what at the end. Okay, so 2 to the power q -1 -1. Okay, so these are, just take average of these values. Okay. Uh, yeah, and so if you take average of these, you will get 7.2. If you take average of these, you will get 10. And if you take average of all of them, I guess you'll take 8.8. Okay. Which of the following is a good strategy for reducing variance in a decision tree? So we discussed this in the last class also, that if you just let's say fix that, okay, after a certain number of subset count, let's say if there are 10 values or 10 rows in the subset, you can stop there and take the let's say the most regression mode, or if it's a regression problem, you can take a mean, right? So just limiting up to, and like up to how many instances you will split again, that can reduce the variance. Okay, so the maximum case would be, let's say, if you allow a leaf node to be created at only one row, right? So that means possible leaf nodes could be your number of data, like cardinality of a data set, right? How many points you have. So that is the overfit version. So to reduce the variance, what you can do, you can conclude to a leaf node after reaching, let's say, a possible k number of data points, right? After you reach k number of data points, you just take a mean or a mode, depending on classification or regression task, right? Okay, that's what they have said. Stop the splitting of a leaf when their number of points has been reached to a threshold k. Okay, or you can also do, let's say, height limitation, right? So you would not let your tree grow beyond, let's say, height of 10, right? That also reduce the variability of the tree, but also so height also depends on how many points you have initially, right? So let's say if you have only 10 points, setting a height of 10 can be seen as a overfitting, or can be seen it's not doing anything to the tree, right? Because there are only 10 data points. But limiting the threshold k, or after how many points you will stop splitting the node, can work in any, let's say, any, like it can work irrespective of the size of the data set. Okay, but thresholding the height can work on a large data set but may not work in a small data set. Okay, these are the following statements about multi-way split in decision tree would categorical feature is correct. So multi-way split always kind of it overfits. So multi-way split means instead of two-way split, so binary split, you split a particular feature in, let's say, 3 ways. Okay, 3 sets, 4 sets. Okay, so that mostly overfit with the data. Okay, so yeah, it can lead to overfitting when dealing with high cardinality categorical features. Yeah, so if there are a lot of possible values in a particular feature, doing a multi-way split can make it very much overfitting. Okay. So 6, which of the following statement about imputation data? Okay, so imputation means you are imputing a missing value with some estimate. Let's say with one value, if you know that my feature has a normal distribution, right? That mean can represent a good estimate. Or let's say I don't know anything, so I can impute that missing part with mode or most repeating values, something like this. Okay, if I know that my data set is skewed, my that feature is skewed, then putting median is a good measure. Or let's say I don't have any idea what the feature looks like in distribution. Then I can go with, let's say, and my segment is very small. I can go with a linear interpolation between two missing ends, right? So what is the option? So mean imputation is always best method. Like there are a lot of imputation methods based on what is your scenario, right? So, but one thing is setting, let's say, one value to all the missing values is not considered a good approach. Okay, sometimes if there are a lot of missing small segments in your feature, you can just impute them with linear, right? Or you can even impute them with forward fill, like whatever was the earlier valid value, you can just fill that entire uh, take subsequent missing values with that earlier missing value. So instead of imputing with one single value as mean, we can impute these different missing segments with different values, right? So it's considered a better approach than mean. So D. So multiple imputation typically produces less biased estimate than a single imputation method, right? So if you can tune, or if you can just adjust your imputed value based on where you are imputing, that is more effective than just imputing the entire feature space with one single value like mean, mode, or median. Okay, and this is just uh, okay, where you would split. So if you just sort the feature F2 and split it where my output has the, so the my resulting entropy of two splits have the biggest difference from the earlier entropy, that would be my answer. Okay, so if I just sort the entire data set with feature 2, right, and I just go over all the points, okay, and see at which point my split represents that my two other output sets would have the less entropy. Okay, so here these 2 points are here, right? So you should just sort them out. So 122 look come something like here top, and then 173. If I just sort it out, it would be very much easy. So let's see if I just copy this doc seats. Okay, can sort it out. Oh, oh, okay. Okay, but you get the point, right? So we cannot copy it into columns. Let me just do one thing. Okay, now we can copy paste it. Okay, now if I just sort it, sorry. Okay, just remove this delete row. Now if I sort just to A to Z, right? Where I should be splitting so that my uh, it's actually very much jumbled up, right? So where I should be splitting so that my data would have the lowest entropy. So by seeing what is the answer, let me see. The answer is C. So 189.2. So I should split here. So this set, this set would be one. Right? This is one set, and this is another set. Okay. So what is the entropy if we can? So one exhaustive thing would be to compute all the possible splits and calculate entropy. But let's just not do that. We just compute entropy for this one. So probability of B here is A is 1, 2, 3, 4, and B is 2, right? So 2 by 6 means 1 by 3, and B has probability of 2 by 3. And here B is 3, 3 by 4, and 1 by 4. If I just go here, compute entropy, here, right? And the entire one, what is the entropy? Oh, its entropy is 1. So both of them are kind of 50-50, right? So what is my gain? So this was my earlier entropy. My gain is how much splitting we are doing? 1, 2, 3, 4, 5, 6. And how much is it? 3, 4, 7, 8, 9, 10. So 6 divided by 10 times is the value plus 4 divided by 10 times 0, 0.8113. So my gain is 1 minus this value, which, yeah, this is my gain. So what you have to do, you have to compute gain for all the possible splits. Okay. So all the possible splits, and better to go with, so it's kind of some practice also where you should split. Okay. So based on this, see here, B is more repeating, right? So, and here A is more repeating. So it's better take if you, so it's very hard to like do it in exam. If like what I would rather do is go with all the calculations for this, but it would take so much time, right? So if you just calculate this entropy for all the splits, possible splits, it will give you that this is the maximum gain you are having. Okay, so that's the answer. Okay, but it is hard to compute this kind of a thing. Okay, computing a base split would require going through all possible splits for that particular feature. But do not, so by looking into this, do not think that, okay, splitting at here would be helpful because it's all B's and all A's here, right? We have to sort it out before computing the gain. Okay, that's the right approach. Okay, now, okay, so week 6, week 5 questions are discussed. Uh, let's go for this week's material. Okay, so we'll first do cross validation. Okay, for a hands-on example of cross validation, and then go for bootstrapping, bagging, these all these concepts and examples. Okay, so cross validation, if you remember, yeah, this was the cross validation logic, right? So if you split numbers, and for all the like for all the cases, one particular splits become the testing set, other remaining sets become the training set, and you take mean of the entire uh, this entire possible test values for all the sets. That's the representative mean of the model performance. Okay, so let's do it. Okay, just let's say oh yes. Okay, let me start. Good. So we'll do cross validation. Let's not write it down. Let's just copy it from one of my GitHub repositories. It's uh, yeah. Time to okay. Okay. So train.py. Uh, so this is the logic. Uh, you just copy paste a few things and then fix the logic. Okay. So scoring. This is the scoring. Let's just take all of them for now. Okay, so let's see. We don't need these, and let's just use the IDs data set we have earlier. Okay, so these things we need train test suite and scaffold stratified k-fold, right? And we already have done train test suite, so we just do k-fold stratified k-fold. Okay, so there is this k-fold also, but stratified k-fold ensures that my data that label distribution is same across all the splits. Okay, 1 2 3 4 5. Let's see if I do 5 split, my label distribution, if there are 5 dog images, then the second set would also have seem like 5 dog images. Okay, similarly like this, so the distribution of the label set would be same. Matplotlib we don't need. Confusion matrix, do you need okay, F1 score, cross validate, confusion matrix. We don't need it for now.
Sir, excuse me, sir.
Yeah, go ahead.
So will they provide any Python environment in that exam, sir?
Uh, so I have to mail to that to instructor for knowing this correctly. But as far as I can tell for now, if there is a Python environment, you will be able to execute that code. Okay, and so if you have to write a code, then you will be able to execute it. Okay, but so from one of my seniors, what I have come to know that this ML course at IIT KGP doesn't take any written, like in the exam, it doesn't take any coding question. Okay, it's mostly MCQs.
Okay, sir.
Okay, but okay, so but if there is coding questions from this IIT Madras course, then you will have the opportunity to run it in that IDE. Okay.
Okay.
Those coding, but I will confirm this. I will email to instructor and confirm this. Now scoring. So scoring means we will try to compute this matrix: accuracy, precision, recall, and F1. Okay. Now let's import our data set iris. Right. So let's just read it from. I guess iris was in week 4 or somewhere, right? Week iris. Yeah, iris dataset iris.c week 4. So you can just take from week 4 iris.csv. Uh, one thing dear, just see what is iris. Okay, so these are my features and this is my label, right? So convert it to df dot drop columns equal to uh, species CIES would give me only the features, and that I can save it at X, and for Y I can just do Y equal to df dot species. Okay, and we have to encode this to a particular let's say what are the species. We can just encode them manually. Y dot unique. Let's say I want to see the unique values. Unique, and this is a function. So these are the unique values, right? I can just have after reading this, I can just have a map. The Setosa, I can mark it as 0. Versicolor, I can mark it as 1. And Virginica, I can mark it as 2. So this is my encoding. Okay. Uh, and after this, I can simply do df dot. So df species is equal to df dot species dot map. So this is my map, which will convert the labels to numbers. Okay. Now if I take y, it's only 1, 2, 3. Y is like an array of this. Okay. So now I have x and y. Uh, so at this point, what we usually do, we do train test split, right? Train test split. But here we will do, instead of train test split, we can do like split k-fold. Okay, k-fold validation. Okay. Now let's see how to code that part. So k-fold stratified k-fold, number of splits are 5. Shuffle equal to true. Okay. So shuffle equal to true, and then random state equal to random state. We can just pick it to be 42. Okay, that's the default random state we mostly have. And then remove all this. We can import any classifier. For example, what are the classifiers we have learned so far? So from sklearn dot tree import this entry classifier. Okay. Uh, entry classifier, and after that, so this is the cross validation code we mostly do. So cross validate this model with the data X and the Y. So cross validation, what is my cross validation split? It is stratified k-fold. Okay, so there are this k-fold also. Okay, so this k-fold thing is also there, but stratified ensures that my label distribution across all the splits are same. So stratified k-fold scoring, I want to calculate these scores, and return training score true means it will also return the training scores. Okay, and these are the validation scores. So if I just run this, and if I check validation scores, these are my validation score. You see there are 5 splits, right? So fit time, this is the time it took for fitting the data. Score time for scoring the testing set, right? Test accuracy, train accuracy, test precision, train precision, test recall, train recall, test F1, train F1. So this is the entire matrix you get for all the training, testing, splits and everything. Okay. So now what will be the reported metrics? Test mean of test metrics, right? So print, so validation scores, we have test accuracy. So it's a array, right? Because there are five such experiments, because there are 5 splits. So x1 become test, x2 become test, x3, x4, x5. Other become training for the respective cases. So we just took np dot mean. So this is my test accuracy. Okay. Similarly, if I want to print other things for the test, let's say test sorry, test f1 would be test f1 precision. You get the idea, right? So these are the different matrices you can print on the test set, but you have to take a mean. Precision recall. So these are the different matrices, but this is not how it is printed actually. See, there are some variance to these values, right? So this is some minor variance based on which split you are testing. There is a minor variance. So sometimes people also add that variance part. So not only the mean value is printed, comma, for the standard deviation you can just do plus minus or let's say um, is sigma would be print, no, let's say plus slash minus, right? Plus minus, and then you have the mean and standard deviation printed. So this is how you mostly report the cross validation accuracies, comma, Stefan precision recall. Yeah. So F1 score is 95% with our test set with a variance of 0.03. So 3% variance is there with 95% F1 score. Okay. Okay, now I guess you know how to cross validate on a data set. Right? Same thing you can also do. So if you want to see what are the training accuracies, you can just put training here, all the places. Train. Now you have the training accuracies. So training accuracies, you can see everything is touching 1 with a plus minus 0 standard deviation. So it's fixed at 1. So all the training accuracies are 1, 1, 1, everything. Okay, I guess it is complete. Now let's see. So there is another let's say class of algorithms after this, let's say decision trees and all, right? These are single classifiers or single regressors. So there are algorithms which basically leverage multiple weak learners, or let's say multiple. So it's like a voting mechanism. So everybody is learning together, okay, on different sets, different views of the data set. Okay, and then when a, let's say, when a predicts, or when a, let's say, query comes in, everybody kind of votes on that query. Okay, whether it is a let's say, if I am talking about the IDs data set, right? So if, let's say I train n number of classifiers, homogeneous classifiers. Okay, if I train n number of homogeneous classifiers, for example decentries, and a new query comes in with all the features, everyone votes on these three classes, these three target classes, and you take the majority. That is known as ensemble learning. Okay, so you basically take vote from multiple weak classifiers uh, that in practice have more generalizable ability, as well as it reduces it can have parallelized implementations, right? So you can query multiple small decision trees at once instead of querying a, let's say, large decision tree, which is kind of sequential in nature, right? So it has two gains. One is it is generalized, so it is more generalizable. It would not overfit. So it is not possible that all the decision trees would overfit the data. Okay, so it is more generalizable, and it is efficient in multi-core environments. If you have a lot of CPU cores, you can train parallelly and also predict parallelly on these small classifiers. Okay, like instead of building a huge decision tree, where I guess huge recently where the generalization capability, like regularizing the model and making it generalized to the data would be very much harder. Okay. Okay. So what are the approaches that were taken for training these small classifiers? These are these. So one thing is this bootstrapping thing. So bootstrapping means, let's say you have a data set, and you bootstrapping means you sample a subset from the data set with replacement. So next time you sample, you can pick up the same data samples. Okay, that is known as bootstrapping. So from a data set, you can pick up two sets with replacement. Okay, not without replacement. So by doing this, what you are ensuring that you can train as many as weak learners as possible. Like if you can train as many weak learners as you want, okay, or weak classifiers as you want, and the sample distribution is same as the true data distribution, because you are drawing with replacement, right? So your sample subset represents the true data distribution. Okay, so bootstrapping is the key to all ensemble methods. Okay, when there are multiple weak learners involved and all. Now there can be two approaches of creating a ensemble classifier. One is this bagging. So what does bagging does? Um, so let's say you have a data set D, and you sample multiple subsets D1, D2, D3, D4, okay, with replacement. So bootstrapping you are doing, you train small classifiers, small n classifiers on those samples, and then whenever you are, let's say, uh, uh, predicting, you are basically taking a vote on all those classifiers. So for classifier 1 to n, whenever a new data comes in, you take predictions from all of them and then take a vote. Okay, this is known as bagging. Okay, and one good example of this black bagging classifier is random forest. So I'll show you. So you have an example plans how the random forest work. So you are basically training, let's say, 5 or 6 small decent trees on the data set, and then taking vote whenever you are, let's say, inferring. Okay, and these subsets can be like overlapping or non-overlapping. There is no hard bound on them. So they are basically uh, sampled with replacement. Okay, so two subsets can have overlap, might not have overlap. It's up to the sampling. Okay, now boosting. So there is, so this is known as bagging. Okay, so you just aggregate from all the predictions, and then okay, now most of my learners or most of my classifiers says this, so this will be my prediction. There is another concept called boosting.
Sir,
What? Yeah,
sir,
go ahead.
is it required to maintain the same size of the data set for your bootstrap data set and original data set?
No. It usually have. So see, if you sample with replacement the entire data set, right? Then you will sample every time the same data set, right? If you sample all the instances, then my sample and my true data would be same, right? So
Okay.
so usually the sample data is less than the true data. That's why I'm saying small learners. So the small learners mean it is trained on a smaller subset of the data set. Okay.
Okay, sir.
Okay. And boosting means you are boosting means actually from one learner you are trying to classify which instances of the training data are hard to classify, and based on that modify my selection at the next classifier. So you basically train multiple classifiers. You just see the workflow. Here from original data, one classifier is trained. It kind of can predict some instances, right? It might not be able to predict other instances. So these are mislabeled instances. So these were basically added to the next. So these datasets were directly added to the next classifier, and then you add some more samples. Okay, so basically whichever samples the first classifier is unable to classify would have more weightage in the next classifier. So next classifier will try to learn whatever the first classifier is not learned. Okay, so these let's say it classifies some instances which the classifier one cannot classify, and again it spits out, let's say, the instances which it finds hard to be classified, right? And then it goes on. So let's say I want to train 10 such classifiers, which from classifier one, whatever it doesn't have, which whatever it is unable to classify, some part of it is classified by classifier 2. Again, for classifier 2, which part of it is hard to classify, that from that set some part is classified by classifier 3, and this chain goes on. Okay, this is called boosting, and one good example would be AdaGrad. There is this classifier called AdaGrad. Okay, so and it can has, so it can have homogeneous as well as heterogeneous models. Okay, so let's say first model is a decentry, next model is SVM or something like this. That things can happen here. Okay, but mostly for this, let's say decision trees and all, it is all the models are homogeneous, they are decision trees. For AdaGrad also all the models are tree based models, but you can always choose something like a unique set of classifiers for a boosting problem or a bagging problem. Okay, this is a kind of concept that is used for training these type of models. Okay, that okay, in boosting we will wait the for the classifier one, whatever data points it is unable to classify would be directly added to the sampled set of the next classifier. Okay, or we will basically add more weights to that those points. Okay, and this trail would go on till you reach the last classifier, and the point is that uh, at the end, at least like, most of the most of the points should be classified by a majority of these classifiers. Okay, because see, it's kind of additive, right? So if it is classified here, it will be likely to classified by all the uh, other classifiers. Okay, so yeah, this is the kind of pictorial representation of this. So bagging is kind of a parallel method. You just take samples, subsamples of the entire data, and then train different models, take a vote. And here you also does the same thing, but here the models kind of fix the previous models inaccuracies, right? So here whatever inaccuracies it would have, that would be acting as the next set of the next model, and whatever inaccuracies it would have, that would be acting as the set of this model, right? And
Sir,
then you
here,
take,
sir,
yeah, go
excuse me,
ahead.
sir. Sir, in the
Go
bagging,
ahead.
can we use the same model or different model, sir?
Yeah, so for models like
Algorithm.
decent for models like random forest, right? They are all decent trees, so they are homogeneous, right? But you can any so the bagging or boosting, both of them, they are agnostic of the model you are using. It's kind of it. See, here we are not specifying whether all of them are heterogeneous or homogeneous, right? So they can have heterogeneous models, but for models like random forest or for models like Adagrad, those are homogeneous and those are tree-based models. Okay, so basically it's a training method you can use for using multiple learners. Okay, okay. So the theoretical idea is clear, I guess. What is bootstrapping? Bootstrapping means you are sampling with replacement, and this can come, okay, this can come in your exam also, that what do you mean by bootstrapping? There can be sampling with replacement, sampling without replacement, sampling uh, half of the samples of the data set. This kind of options can be there. Okay, so the right option is sampling with replacement. Yes, and the one thing is the sample size should be always less than the uh, the total data size. Okay, why? Because otherwise it doesn't make sense, right? If I sample with replacement and I don't sample, or I sample all the data points, then my entire sampling, like different samples, would be same. Okay, now bagging boosting, you got the idea that bagging means you are bootstrapping, then training all the models and then taking a vote. Boosting means you are taking a sample, or let's say taking the entire sample, and then you're not actually bootstrapping. Okay, so in boosting, you are taking the entire sample and then training a classifier. Whatever it misclassify, you give it to the next model for classifying, right? That loops goes on until all the data points can be classified at least by one classifier. Okay, okay, so just do some examples. Ranking boosting, it's two. Uh, or we we have this data set, right? Uh, where was the data set? Yeah, this was the data set, right? Rain or not rain. So, okay, we can just copy the entire processing code and all from here. This is ensemble. Wait a bit. Ensemble classifiers. So this is the data processing part. We just take the data. These are the columns, and now this is my clean data. Yeah, then formatting according to the dates. So what we are doing, we are we are formatting our data to see whether a particular day would have rain or snow, right? From the previous class, if you remember. So this participation type, this is rain or snow. So rain and snow instances are there. X featured, X label. So we cast rain to be 1 and snow to be 0. And now our ensemble model part is here. So similarly, you can do train test split, and let's just go with normal train test split. Okay, not with train validation and test. So instead of remainder, it will be test. 30% test set sub satisfy Y means my test set would have the same label distribution. My classification function. So it produces from Y prediction and Y produces all the possible uh, matrices, right? It prints all the possible matrices. So now instead of doing the see earlier we were importing this decision tree classifier, which is kind of a it's a like one classifier, right? Now for importing any ensemble classifier, this ensemble package is there. Import and see these are all ensemble classifiers you have. Okay, now where is my random forest classifier? So this is an bagging classifier. Okay, so RF model, or let's keep it model, is equal to random forest classifier and number of estimators. See this number of estimators 100. That means it will create at max create 100 estimators. First 100 these entries. Let's limit it. Let's not go with 100 these entries. Let's just go with let's say 5 these entries. Okay, and there are no other bounds. Like what is the maximum height of the tree? What is the minimum number of samples at the leaf nodes? We don't set those limits for now. Model.fit extend white trend. We have the model. Let's see how to print a decision tree random forest. Uh, Printing would not work.
Assignment programs also.
There should be some way. So earlier we have seen that plot. There is this plot function by which you can print these entries. Okay. So how we can access individual these entries are like this. Model dot estimators underscore 0. Estimators. So this is a decentry list, right? So these are the different decentry lists. And then I can take the 0th decentry. I can print it with that earlier print function. And let's see how this is how we can cn equal to data feature name. So cn, where the cn is used. cfn cn feature names. Oh, these are not required. Okay, let's just use this entire code. We can. Okay, so figure rows 1, columns 5, figure 9 dpi, fine. Tree estimated index. We don't need this. We don't not need this either. Fill this access index. Access set estimator. Let's not save it. So PLT is not there. I plot as PLT. Okay, tree dot plot. So from sklearn dot tree import dot tree. Now RF now. So it will be for us, it is model. Yeah. So this is what our these 5 estimators we have created from our data. So this is our this estimators. Okay. So this is model 1, model 2, model 3, model 4, model 5. of that random forest. These are different decision trees. Okay. Now let's evaluate our model now. So this is our model. Uh, to evaluate, what you have to do, we can just copy it from here. So training set evaluation is this. So instead will not fit it. Predict on the training set, calculate all the matrices and print. DT, where is DT? DT, no, it's model. Yeah. So this is our training accuracy. 0.99 is the precision, accuracy is 0.998 F1 score, and then the classification report is almost perfect. Confusion matrix, you can see only one and only total 3 misclassifications are there. Now what is for the testing? So you can just replace everything with test. For testing, my accuracy is 0.98 and it's mostly 16 misclassification. It's quite good. So if one score 0.98 means it's quite good. Okay. What was our accuracy for the earlier model? For the decision tree model, it was if one score was 0.984. For the ensemble model, it is 0.986, right? So it's more generalized. It's not that much, it's 0.4%, but it is still there is some gain. Okay. Okay, so this is how random forest models work. Now let's see from sklearn. So there learn dot ensemble import. This is bagging classifier and boosting classifier. I have never used them. Let's see what they have. Bagging classifier, what it takes and what it has. See, in bagging classifier, it takes the estimator, right? It takes the estimator class and the number of estimators. So it's a homogeneous. So we can create the same. So for example, if I want to, so is it a function? So let's see. What is this estimator? It's an object based estimator to fit on the random data set. So what would be an example of based estimator? Ensemble import. It's a decision tree class. Sorry, not an ensemble. Let's say tree. Let's not take tree. Let's take SVM. Okay. Import SVC. Now estimators equal to SVC, and then you can set up all the parameters here and everything. Okay, base estimator. Let's just keep it plain. Number of estimators, I can take it as 10, and any other thing. Or let's give it 5. Let's go for 10. Oh, earlier did we have 5 or 10? Oh, we had 5 estimators. Okay, fine. 5 estimators, and this is our model, right? Now model dot estimators, estimators. Can we access them? Oh, it's not fitted. Wasted random state. Okay, so here you cannot access. Oh, no, number of estimators we can access. Maybe after fitting we can access. So dot fit next train, y train. So estimated is this tracking classifier. My estimated is SVC. Okay, so this series estimators list, it creates 1, 2, 3, 4, 5, 6 estimators with different random seeds. So different random seeds ensure that my model would converge to different points. Okay, and it is also set with different samples of the data set, right? So that means these models are not same, they are different. Okay. Okay, so we can also train a bagging classifier based on SVC. Similarly, for boosting, let's see what we can do with boosting. Scalar.n sample. Okay, so we can only have bagging classifier because they can be homogeneous. Okay, so bagging is mostly homogeneous. Here, bagging classifier, bagging regressor. But boosting, for boosting, we can have homogeneous as well as heterogeneous model, right? So one good example would be this ADA boost classifier. This does boosting on recent trees. Okay, so let's see. Del equal to ADA boost classifiers, estimators, and number of estimators. So estimator, I want to give, let's say, SVC. Same, I want to have models that have SVCs. SVC, number of estimators 5. Same model dot fit train retrain. So data boost with algorithm SNR requires the weak learners, supports the calculation classifiability with probability method. Please change the base estimator or set this algorithm as this. Okay, so now my model has been trained. Model dot estimators. You can see these are, there is only one model. Number of estimators 5. Okay, yes, same means I I guess we have to do decentralized classifiers and not use the same algorithm. Same means it's kind of training on the same classifier. Is it? Number of estimators. Okay, so I'm a bit confused on why it is not printing 5 days entries. Anyway, so we'll check and later on I'll update it this. Okay. Okay, this is how adapt. Sorry, let me undo this. Undo delete cells. This is how adapt classifier is also work. This one also works. So it basically takes that boosting logic into this type of a decent tree or any classifier. In classifiers, learning date, CMR random state, base system, deprecated. Okay. So maybe I have to check it how it is representing the learners in this class, model class. I have to check it. I'll update in the slide. Okay, and another classifier is there that is called voting classifier. Scalar dot ensemble voting classifier. Okay, now let's see how this voting classifier is used. Here you see there are estimators, right? So it's basically the aggregation function. So what is it? It is basically this aggregation function. So you pass the different models you have, right? And then voting hard means so hard means it will take majority. That's it. And for either a soft voting soft and other things. So what are the other uh, options for voting? Hard means it will take majority. Okay, soft means voting. So it's soft, right? Soft means it predicts the class level based on else if soft predicts the class level based on arguments of the sum of the predicted probabilities, which is recommended for ensemble methods of well calibrated estimators. Okay. So basically, how much one is confident, it will predict based on that confidence, based on the probability scores. Okay. Not like if it is more than 50, take 1, less than 50, take 0. Okay. So what you can do, let's say how you can use this. Okay. Uh, let's say I have three models. Model 1 to be a decision tree. Model 2 to be a SVM, SBC. Model 3 to be a, let's say, what you can use, a random forest, right? We fit on these three models are the same data. Model 1 dot fit x train y train, and just copy paste this line three times for model 2, model 3, trained, right? All the models are trained. Now I can do a voting classifier on these three models. What I have to pass, I can also pass weights. So let's say I trust the model 3 more, so I can pass this model 3 weights to be higher. Let's say I pass 1 1 3, right? So it trust the model 3 three times than model 1 and model 2. Okay, in jobs mean how many parallel jobs you can run. So if I'm predicting on 3-core CPU, right, or a 4-core CPU, if my n jobs is 3, I can predict on parallelly on three classifiers. Okay, so in estimators I can pass to be a list of model 1, model 2, model 3, right? Now my model looks like this. See, it's a voting classifier among the decentrally SVM and random forest. Now, if I want to test its accuracy on training set and testing set, I can just do a copy. But the voting classifier instance is not filled yet. It call fit to okay. So instead of okay. So instead of fitting them separately, I can just okay. So one thing I forgot. Okay. Okay, so instead of fitting them separately, what I can do, I can just instantiate them, create a voting classifier, and then fit the entire classifier at once. Okay, model.fit x train y train, and then what does it say? Descent tree is an object not iterable. Descent tree classifier is object is not iterable. Okay, estimators. Okay, why is it so? Descent tree it is not iterable. Okay. Maybe we are doing something. Not passing the parameters properly. Let me check how we are supposed to pass parameters. Voting classifier. Okay, so we should be passing estimators like this with names. That's good. Not like a list. We should be passing a list of tuples like this. Okay. So the first model is DT, model 1. Then ASVC, model 2. And then a random forest model, which is model 3. Now my model is okay. So now see my model looks like this. So ADT, ASVC and RF, this is a voting classifier and it takes vote from all of them. And my voting uh, regime is like hard by default. Okay, so it takes majority. Now if so my model is currently trained. If I predict its training accuracy, it's all one, right? Now if I just copy this, this is the testing one, right? So Yeah, so this is the testing accuracy. This 988, so it's more accurate. It's more accurate than going with only these entries or only SVMs or SBCs and all, right? 998. So we are like earlier with one decentry we can achieve only 984. So we have 0 point, we have around 4%, four, not 4%, we have 0.4% improvement on our accuracy. Okay. You get the point, right? How these models can be coded and everything. So let's see whether we can decode the boosting classifier or not. Okay, sklearn boosting classifier. Okay, gradient boosting classifier. Fine. Yeah. So how we should use it? Okay. Let's see whether all the classifiers are same recent trees or not. Okay. So gradient boosting classifier, number of estimators we can give. What are the estimators? It is, I guess, it's a in each stage n classes regression trees are fit regression trees. Okay. So more decision trees, they fit decision trees. That's it. So in estimator, let's say 5. Okay, model, and then we can just fit. Fine. Now my model should have this estimators function, estimators, and you see they are decentralized regressors, nothing else, right? So gradient boosting classifier creates 1, 2, 3, 4, 5 decentralized regressors. Okay. Is it array of dot? If I create shape, it's a column vector of this. Okay, if I want to print them, I can do. I can use the previous printing here. And index comma 1, the estimator run. Index, oh, sorry. Index, this one should be 0. Yeah, so these are the these are the different estimators that this model built. We can save it and explore whether they are separate on, right? Let's explore. This is a gradient boosting classifier. Save. It's being saved at 900 dpi, so it should be pretty clear. Uh, okay. It's not loading in my browser. Let me open it up from here. Yeah, this here, right? So you can zoom in. Yeah, I can zoom in pretty. Let's see here, right? X0 less than 555. Okay, here. Yeah, the trees are not same, right? See here, it is X7, it is X0, right? So the trees are not same. They're different, but maybe for the first split, it is same. For the first split, it is same, almost same, not exactly same. Here the split is different. Here the split is again different. Okay, so they are not same. They are basically different estimators. Okay, and so what would happen that this classifier, whatever it is not confident about, right? Whatever it is, let's say less confident, it gets so if it is confident, then my prediction ends here, right? And if it is not confident, that it goes to the next estimator and see what is the confidence of that prediction. Again, it will, if it is not confident, it will go to the second estimator. That is how the boosting classifiers are trained, right? So whichever is misclassified the first estimator will be goes to the second estimator. Second, whichever is misclassified by the second estimator, misclassified means it is less confident about the prediction, right? Okay, and then the misclassified instances would be goes to the second estimator like this. So until I have a good confidence, my this classifiers would be triggered in a subsequent fashion. Okay. Okay, so you get the idea. Uh, so what was our goal? Okay, so we have the random forest example and all. So do you have any questions for
Am I
this
audible?
week's material or from previous week's material?
Am I audible?
And don't worry, I'll share this week 7 code. So if you can, if you want, you can play around and see whether you can, you can just play around and see whether you can just train another other classifiers on other data sets. Okay. Guys, if you have any doubts on the cross validation or how it is, how bootstrapping works or backing works, you can ask now. Okay, so let's go for the second from the previous weeks also. If you have any doubts on desentry or regress entry or anything about, let's say, neural networks, you can ask. We have around 10 minutes of time.
Sir, may I ask a question, please?
Yeah, go ahead.
Actually, these programs which you are doing, no?
Yeah.
Will you be uploading that also along with the assignments?
Yeah. So it is actually there. So you can find it here, codes. Right. So I guess
Okay.
in the post I have also shared this link, this drive link. So previous questions will be accessed here, week 1 to week 6, and for the codes you can go to this codes folder. Up to week 6 it is uploaded. I will upload week 7's code after the call.
Okay, that's fine. Thank you.
Yeah.
Thank you.
Any other questions? Okay, so let's see what is next week's. Let's do the next week's planning. Okay, so for next week we will be, and remember the next week class will be on 11th March. Okay, because I will be traveling from 14th March to 22nd, 24th March. Okay, so 15th class would be taken on 11th, and 22nd class will be taken on 28th. Okay. So by the way, so what we will learn in the next call would be uh, gradient boosting. So the model we have already seen. We'll see what gradient boosting is. Okay, and then random forests. So random forest, I guess you already know. Multi-class classification means when you have multiple classes to classify. That's very like naive topic. So instead of 2 classes, you have multiple classes. That's it. Okay. Uh, Naive Bayes classifier and Bayesian network. So naive Bayes classifier is Bayesian network is something like new. Okay, but naive Bayes classifiers are just like if you have a evidence, or let's say if you have a data set, you compute the evidence, the uh, prior and the likelihood of a particular event, you can just multiply and compute the posterior, right? So given a particular X, what is the probability of Y? Okay, so that's what naive Bayes means. So yeah, so, and Bayesian networks is new, so maybe we'll start with Bayesian networks, then this HMM and this graphical models. Okay, so these are new things. So just to give you a hint, but they are basically models that predicts on a temporal basis. They predict what is the probability of a particular event happening given a chain of events. So if you have a chain of events, okay, I wake up, I brush my teeth, I take my breakfast. What is the probability of me being uh, me being going to class, something like this. Okay, so based on a chain of events, uh, what is my next probability of all possible events? That's what this HMMs and all things are. Okay. Okay, it's almost, I guess, these things we can cover. Bridge algorithm, this clustering algorithms are there. GMMs, expectation minimization is a good thing. And then last week we have reinforcement learning. Fine. Okay. So next day, I guess we will start with Bayesian networks and the corresponding assignment questions will be. Okay.
Actually, are we expected to be proficient in Python for this course?
So see, not proficient. I would say you should remember the very basic paths. So very basic paths for, let's say, if you are supposed, so it can happen that you are supposed to run a small snippet of code and let's say tick the output, right? What would be the possible outputs? Or let's
Okay,
say
okay.
there is a code snippet given. You are supposed to predict what will be
So,
the
as you
output.
mentioned earlier during the class, sometimes that programming part may not be there for us.
Yeah, yeah.
But
Maybe
it
it
will
can
not
happen
all
that,
be. It will not all be multiple choice. I think no, because that
yeah. So
in the
it
website it is given that other types
it
can also be there. I think we got a mail
exactly.
also.
Exactly. So there can be small code snippets also that you have to code, or you might have to predict its output.
But
So
they
let's
did not
say,
mention coding, sir. Actually, they have mentioned, I think, fill in the blanks kind of questions only.
yeah,
I don't
exactly.
know whether they have mentioned coding because
Yeah.
we got something on our wherever that Swayam site is there. No, they had
Mhm.
mentioned something. I don't remember seeing programming there.
Okay.
But
So
maybe,
one
as you
thing I
said,
can
they may be asking us to
fill in
evaluate
the
that
blanks.
output of
Yeah.
the code or something. That way they may say,
Exactly.
okay, that way.
Exactly. The fill in the blanks question can be very common for the final exams. But one thing I can confirm with the instructor is whether there will be any coding ID
Programming.
available during the test, right? So
Because
from
not everybody may be working on Python. So if we are
exactly,
asked to program, if we have internet, we can do. But otherwise,
exactly,
no, I don't know how we will know all the commands by
exactly.
all.
So
So many
that
classifiers are there.
yeah,
But
that's fine. That's
actually,
fine.
for all these classifiers, when you selected one command, it was showing all the arguments. You know, how did you do that actually?
Okay,
When you
that's actually this ID I'm using. Okay, so it is Jupyter Notebooks
Jupyter.
feature.
Okay, that is
Yeah.
okay. But always,
So
even if internet is not there during an exam environment, also, will these
yeah,
arguments
no,
be visible?
no, 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 no,
That's
no.
what. Okay.
So you see, if I do Shift tab after this bracket star, right? If I do Shift tab, I can have this pop up of all the parameters and everything.
Okay. And what about how do you auto complete some keywords you're auto completing? No, how did
Yeah,
you
so
do that?
that's tab. So it's, let's say I want to
Tab. Okay.
autocomplete n estimators, right? N estimator and then do tab, it will autocomplete the
Okay. 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 Thanks.
first hit. So
Okay. Okay.
this
Thanks.
ID has those features for
Uh-huh.
quickly writing code and all, but it will not be available during any exams.
So
So
we may not get this Jupyter ID itself for that
no,
exam.
no,
That's
no,
what it.
no, no,
Okay.
no.
Okay. Okay, sir. Thank you. Okay.
Okay, then see you in the next class. I guess if no, if you have any doubts, I can clarify it now. Otherwise, we can just meet directly in the next class and discuss Bayesian networks. Okay.
But actually, when you come for the next class, no, whether all the lectures we should be knowing, because I don't know whether by that time everything will be available or we would have
No,
finished.
no, even if it is not, so even if you have not listened to the lectures for Bayesian network, I will start with a basic
Okay.
theory, then
So you will
we'll
be
progress
covering
on
in that
coding and
way.
all.
Or you will be covering in that way. Okay, that's fine.
Exactly.
Okay, thanks. Okay.
Okay,
Thanks. Okay.
stop sharing. Okay, guys, any questions? So by the way, I will share all the resources in the WhatsApp group. So if you are not there in the WhatsApp group, you just join there.
Yeah, I am there, I think, already.
Okay.
It's okay. So thank you.
Thank you.
Thank you, sir.
See, I'm closing the stop recording. Yes.